Intro. Right now, 400 million miles from Earth, a storm larger than our entire planet has been raging for over 350 years, longer than the United States has existed. The Great Red Spot on Jupiter generates winds of 400 miles per hour that could obliterate everything in their path. Yet this cosmic hurricane maintains perfect stability in an environment of absolute chaos. But here's the terrifying truth. This ancient storm is dying, shrinking at 580 miles per year, and when it finally disappears, Jupiter will never be the same again. Did you know that we're literally watching the death of a weather system older than human civilization unfold in real time? The mystery storm discovery. When Juno reached Jupiter's North Pole in July 2016, mission control went dead silent. What they saw defied every computer model, every prediction, every theory about gas giant atmospheres. 8 massive cyclones, each the size of Texas, were arranged in a perfect geometric pattern around a central hurricane that could swallow Earth whole. These weren't ordinary storms. They were maintaining positions with mathematical precision that seemed almost artificial. The southern pole revealed an equally bizarre sight. 6 cyclones locked in a pentagonal formation, spinning at 100 miles per hour while staying 52 degrees Fahrenheit cooler than their surroundings. What terrified scientists most was the stability. On Earth, hurricanes last days or weeks before dissipating. These Jovian monsters have been maintaining their cosmic dance for years, possibly centuries. The Deep Space Network tracking data showed these cyclones weren't just surface features. They were connected to atmospheric rivers flowing thousands of miles deep. It's as if Jupiter operates by entirely different laws of physics, where chaos organizes itself into patterns that shouldn't exist according to everything we understand about planetary atmospheres. Largest eruption recording. The microwave radiometer aboard Juno penetrated deeper into Jupiter than any instrument ever had, and what it found was absolutely mind-bending. Hidden beneath the cloud tops were towering atmospheric structures that scientists dubbed steeple mountains. Invisible giants of gas and energy extending 1,800 miles down into the planet's interior. To comprehend this scale, that's 270 times deeper than Earth's Mariana Trench. These weren't physical mountains but massive atmospheric belts that plunge into Jupiter's core like cosmic elevator shafts. The gravitational measurements from Juno's 54th flyby on September 7, 2003 revealed the shocking truth. Jupiter's atmosphere doesn't end where we thought it did. Instead, it blends seamlessly with the planet's interior in a way that violates our basic understanding of planetary structure. The spacecraft used Jupiter's own gravity as a scanning tool, measuring velocity changes as small as 0.01 millimeter per second from over 400 million miles away. What emerged was a 3-dimensional map of a world where the boundary between atmosphere and interior simply doesn't exist. Jupiter isn't just a gas giant with a solid core, it's a fluid, chaotic system where atmospheric storms reach depths that would take you from New York to the center of Earth and back again. Largest eruption recording. Juno uncovered evidence of atmospheric eruptions so massive they make Earth's most violent volcanic explosions look like firecracker pops. The Great Red Spot, that iconic crimson hurricane we've admired for centuries, plunges an astounding 300 miles below the cloud surface, deeper than the distance from Earth to the International Space Station. But this ancient storm, observed since the mid-1600s, is just one player in a symphony of atmospheric violence. Smaller storms reach 60 miles down, while others extend over 200 miles into Jupiter's interior, creating a labyrinthine network of atmospheric chaos that operates in 3 dimensions. The energy scales involved are beyond human comprehension. These storms have been raging for millennia, powered by forces that dwarf anything in our solar system. NASA's precision instruments detected atmospheric explosions that release more energy in a single event than Earth receives from the Sun in an entire year. The Deep Space Network measured these eruptions with incredible accuracy, revealing that Jupiter's weather system isn't just more violent than Earth's, it operates on completely different principles. While our storms are temporary disturbances in a stable atmosphere, Jupiter's storms are permanent features of a world in constant atmospheric rebellion against the laws of physics as we understand them. Jupiter's magnetic field. The magnetometer investigation aboard Juno revealed that Jupiter's magnetic field is not just stronger than expected, it's completely alien in structure. Jack Connerny from NASA's Goddard Space Flight Center led the team that created the most detailed magnetic map ever made of another planet, using data from 32 orbits around the gas giant. What they discovered was terrifying. A magnetic field more than twice as powerful as models predicted, with an irregular, chaotic structure unlike anything seen before. The most unsettling discovery was the Great Blue Spot, a massive magnetic anomaly at Jupiter's equator that's drifting eastward at 2 inches per second, completing a full lap around the planet every 350 years. This isn't just a magnetic field, it's a cosmic scar. Scientists believe meteorite impacts billions of years ago modified Jupiter's magnetic structure, which is now frozen in a superconducting core, like a permanent record of ancient cosmic violence. Even more disturbing is the discovery of secular variation. The magnetic field is changing over time, something previously only detected on Earth. Jupiter carries the magnetic memory of collisions that happened when the solar system was young and chaotic, making the planet a living museum of cosmic catastrophes that shaped the worlds we see today. Atmospheric water mystery. Juno's microwave radiometer has been conducting the ultimate planetary autopsy, using 6 antennas to X-ray hundreds of kilometers below Jupiter's cloud tops. And what it's finding about water content is rewriting the textbooks on planetary formation. For decades, scientists assumed Jupiter formed beyond the frost line where water should freeze and accumulate in massive quantities. The planet should be soaked with water vapor, but Juno's measurements are revealing a distribution so patchy and unpredictable that it's forcing us to reconsider everything about how gas giants form. The water mystery cuts to the heart of solar system formation theory. If Jupiter's water content doesn't match our models, it suggests the early solar system was far more violent and chaotic than we ever imagined. The implications are staggering. It could mean that planets don't grow peacefully by accumulating material, but are forged in cosmic disasters that fundamentally alter their composition. Juno's deep atmospheric scans are essentially performing cosmic archaeology, peering into Jupiter's interior to read the story of its formation, written in water vapor concentrations. What they're finding suggests that Jupiter didn't form where we think it did, or that massive collisions during its formation scattered water in ways that defy current planetary formation models. The planet is keeping secrets about the early solar system that could change our understanding of how Earth and every other world came to exist. Polar cyclone dynamics. The poles of Jupiter are cosmic madness manifested in 9 cyclones arranged in perfect geometric symmetry around the North Pole, 6 cyclones forming a pristine pentagon around the south. NASA's navigators have been tracking these atmospheric beasts with surgical precision since Juno's arrival in July 2016, and what they've discovered violates every principle of atmospheric dynamics we know. Each cyclone spans nearly the width of the continental United States, spinning at incredible velocities while maintaining their positions like cosmic clockwork. On Earth, storms are temporary chaos that forms and dissipates. But Jupiter's polar cyclones have been locked in their geometric dance for years, possibly centuries. They resist change with an almost intelligent stubbornness, forming what scientists describe as a private club that seem to resist new members. The data reveals these aren't just surface storms, they're massive atmospheric columns extending thousands of miles into Jupiter's interior, connected to the planet's deep atmospheric rivers like cosmic pillars holding up the sky. The precision of their arrangement suggests forces at work that we don't understand, atmospheric dynamics operating on scales and timescales that make Earth's weather look like child's play. These cyclones are essentially atmospheric monuments, permanent fixtures in a world where chaos has somehow organized itself into mathematical perfection that shouldn't be possible according to everything we know about fluid dynamics and planetary atmospheres. Jupiter's composition and structure. Juno's gravitational measurements have shattered our most fundamental assumptions about Jupiter's interior structure. The spacecraft has revealed that the king of planets doesn't have a solid core like textbooks claim. Instead, it harbors a fuzzy core made of rock fragments and metallic hydrogen scattered throughout its interior like cosmic shrapnel. This discovery is revolutionary because it suggests Jupiter's formation was catastrophically violent, likely the result of a massive collision that occurred during the early solar system's chaotic youth. Juno acts like a cosmic detective, using tiny velocity changes to map the distribution of mass inside Jupiter. By measuring gravitational variations as small as 0.01 millimeter per second from hundreds of millions of miles away, scientists can essentially see through the planet's layers. What they're finding is that Jupiter's interior is not the neat, layered structure we expected. It's a chaotic mixture where different materials are scattered in patterns that speak of ancient violence. The implications are staggering. If Jupiter was fundamentally altered by a collision, it means planetary formation in our solar system was far more destructive than we thought. Planets aren't just peaceful accumulations of cosmic dust and gas, they're the survivors of cosmic wars fought billions of years ago, carrying the scars of impacts so massive they can reshape entire worlds and alter the course of planetary evolution forever. Great Red Spot Analysis. The Great Red Spot has been Jupiter's most iconic feature since telescopes first revealed it in the mid-1600s, but Juno's close-up analysis has unveiled a storm so complex and alien that it's forcing us to redefine what we thought we knew about atmospheric phenomena. This isn't just a hurricane, it's a 300-mile-deep atmospheric monster that extends from the cloud tops down into Jupiter's interior, further than the distance from Earth's surface to the International Space Station. Juno's instruments have mapped the storm's three-dimensional structure, revealing a spiraling tower of gas and energy that operates like a cosmic tornado lying on its side. The storm's winds reach speeds that would instantly destroy anything on Earth, while temperatures and pressures at its base approach conditions found in the cores of rocky planets. What makes the Great Red Spot truly terrifying is its permanence. This storm has been raging continuously for over 400 years, possibly much longer. It's a weather system older than most human civilizations, powered by energy sources we're only beginning to understand. Juno's data reveals that the spot is connected to Jupiter's deep atmospheric layers, drawing energy from the planet's interior heat like a cosmic engine that never stops running. The storm is essentially a window into Jupiter's soul, a permanent scar in the atmosphere that reveals the violent, chaotic nature of a world where weather operates on scales and timescales that dwarf anything in human experience. Jupiter as planetary protector. Juno has documented Jupiter's role as our solar system's bodyguard in terrifying detail, revealing a cosmic protector that's constantly under siege from interplanetary debris. The spacecraft observed a meteor impact in April 2020 with an estimated mass of 250 to 5,000 kilograms, just one of countless projectiles that Jupiter's massive gravitational field captures before they can hurtle toward the inner solar system. Without this cosmic vacuum cleaner, Earth would face regular bombardment from asteroids and comets, making complex life nearly impossible. Juno's observations show that Jupiter is essentially sacrificing itself for the rest of us, taking hit after hit from space rocks while we orbit safely in the inner solar system. Each impact creates massive explosions visible from hundreds of millions of miles away, releasing energy equivalent to multiple nuclear weapons. The planet's gravitational influence extends far beyond its physical size, reaching out like invisible tentacles to snare dangerous objects that might otherwise threaten Earth. But this protection comes at a cost. Jupiter is constantly being bombarded, its atmosphere churned by impacts that would sterilize entire continents on Earth. The planet stands as a cosmic shield between us and the chaos of deep space, a guardian world that absorbs the violence of our solar system's debris-filled void. Juno's documentation of this protective role reveals that our existence might depend entirely on Jupiter's willingness to serve as the solar system's punching bag, standing between civilization and cosmic annihilation. Jupiter's magnetic field. The death of Jupiter's most famous storm is happening before our eyes, and Juno has given us ringside seats to watch a cosmic legend fade away. Amy Simon from NASA's Goddard Space Flight Center has been tracking the Great Red Spot's decline using Hubble Space Telescope observations, documenting a shrinkage so dramatic it's rewriting our understanding of atmospheric longevity. The spot has contracted from 25,500 miles across in the late 1800s to just 10,250 miles today, less than half its historical size. Beginning in 2012, amateur astronomers noticed the shrinkage accelerating to an alarming 580 miles per year, transforming the storm from an oval to a circle as it literally starves to death. Yale PhD student Caleb Kevaney and his team have developed computer models showing that the Great Red Spot is essentially eating itself, Smaller storms that once fed it energy are becoming less frequent, leaving the giant hurricane to slowly consume its own substance like a cosmic Ouroboros. Their simulations predict the spot could shrink to nothing in approximately 2.6 Earth years, marking the end of a weather system older than human civilization. The implications go far beyond losing a famous landmark. The Great Red Spot plays a crucial role in Jupiter's atmospheric dynamics, and its disappearance could trigger changes throughout the planet's entire weather system. We're witnessing the transformation of Jupiter itself, watching a world that has remained essentially unchanged for centuries suddenly evolve before our eyes as its most iconic feature slowly fades into cosmic history. That's the incredible reality of Jupiter, a world so alien and violent that it challenges everything we thought we knew about planetary science. Juno's mission officially ends in September 2025, but the mysteries it has uncovered will keep scientists busy for decades. From dying storms to magnetic anomalies that defy physics, Jupiter continues to prove that our universe is far stranger and more terrifying than we ever imagined. What discovery shocked you the most? Drop your thoughts in the comments below. If you're fascinated by the cosmic mysteries lurking in our solar system, make sure to hit that subscribe button and ring the bell icon so you never miss another mind-blowing episode from Space Facts. Until next time, keep looking up. A Harvard scientist is sounding the alarm. An interstellar visitor, 3I Atlas, is shedding metallic alloys that just shouldn't exist. Real data from our best telescopes shows atomized nickel streaming from its core, but with practically zero iron. A chemical fingerprint that really defies everything we know. Harvard's Avi Loeb is asking the question no one else wants to: if these metals aren't natural, what does that mean? The answer could upend our place in the universe, so let's explore this together. The discovery of 3I Atlas. What would you do if you saw something moving at 130,000 miles per hour that wasn't supposed to be there? On July 1st, 2025, the Atlas survey team in Chile spotted a faint, fast-moving speck. The math instantly told a story that just didn't fit any known playbook. Its path wasn't just a long loop, it was hyperbolic, with an extreme eccentricity that confirmed it was a visitor from deep space, moving too fast for the sun to ever capture it. This wasn't a comet on a return trip. Astronomers combed through archival data and found earlier images, firming up its trajectory. The object was born far beyond our solar system, possibly somewhere near the galactic center. By the time it was discovered, it was already inside Jupiter's orbit, making a one-time slingshot around our sun before it shoots back into the void. Its incredible velocity confirmed it. 3I Atlas is only the third confirmed interstellar object ever seen, a messenger from another star that will never return. This isn't just a rock, it's a clue from an unknown part of the galaxy. The nickel mystery. Imagine finding a fingerprint that doesn't match any person on Earth. That's what astronomers found in the light from 3I Atlas. Almost as soon as it crossed Jupiter's orbit, spectrographs detected strong signals of atomic nickel streaming from its coma. But the real shock wasn't what was there, it was what was missing. There was virtually no iron. This isn't just unusual, it's chemically bizarre. In every meteorite and comet we've ever studied, nickel and iron are cosmic partners, forged together in the hearts of dying stars and locked into the same minerals. When a comet heats up, they should be released together. Yet, data from the Very Large Telescope showed nickel vaporizing off the object, while iron was a no-show. Harvard astrophysicist Avi Loeb was the first to publicly highlight how unnatural this is. He argues that separating nickel from iron requires industrial processes here on Earth. In space, it's unheard of. It's like finding a gold ring without any trace of the other metals typically alloyed with it. This single chemical clue is so potent that it forces a profound question. Are we witnessing a freak of nature, or is this a deliberate engineered signature? Carbon dioxide dominance. Just when the nickel-iron problem had scientists scrambling, the James Webb Space Telescope delivered another bombshell. Pointing its powerful infrared instruments at 3I Atlas, a team of astronomers analyzed the gases in its coma, and found that carbon dioxide was completely dominating the mix. The measured carbon dioxide to water ratio was a staggering 8-to-1, the highest ever recorded for any comet, whether from our solar system or beyond. To put that in perspective, typical solar system comets have CO2 levels around 4% of their water content. Here, CO2 is the main ingredient. This wasn't a fluke. The readings remained consistent across multiple observation sessions as the object neared the sun. While other gases like carbon monoxide were present, nothing came close to the CO2 spike. This kind of chemistry just doesn't align with our models of comet formation. Some researchers propose that its unique composition is the result of being cooked by cosmic rays over a billion-year journey. Others wonder if it's a clue to the specific conditions of its home star system. But the question remains, does this unprecedented chemistry point to nature at its most extreme, or is it another sign that something else is at play? The Oumuamua precedent. This isn't the first time an interstellar visitor has broken all the rules. Back in late 2017, astronomers detected one Oumuamua. At first it seemed like an asteroid, but its behavior was deeply strange. As it swung past the sun, it began to accelerate, pushed by a force that wasn't gravity. The problem? There was no visible outgassing, no tail, no coma, none of the typical rocket-like effects a comet uses to speed up. Oumuamua left nothing behind. Its light curve also suggested a bizarre shape, perhaps 10 times longer than it was wide, like a cigar or a flat pancake. The scientific community scrambled for an explanation: exotic ices, hydrogen outgassing, fractal dust. But no single natural theory fit all the data. It was into this debate that Harvard's Avi Loeb stepped, arguing that Oumuamua's shape and acceleration were consistent with an artificial object, specifically an ultra-thin solar sail designed to ride the pressure of starlight. The idea caused a firestorm, but it cemented a critical precedent. When objects from other stars arrive, we shouldn't assume they'll play by our rules. Oumuamua prepared the scientific world to ask bolder questions. Ancient sky metal. Humanity's fascination with metals that fall from the sky is not new, it's ancient. Over 5,000 years ago in ancient Egypt, craftsmen hammered tiny beads from a mysterious iron that they didn't mine from the earth. Modern analysis of these beads from the Gerza cemetery reveals a nickel content of nearly 30%, far higher than any terrestrial ore. This was the unmistakable signature of meteoritic iron. The story gets even more incredible with the dagger found in the tomb of King Tutankhamun. Discovered in 1925, the pristine iron blade was a mystery for decades. Finally, X-ray analysis confirmed its celestial origin. The blade contained 11% nickel and traces of cobalt, a composition that matched iron meteorites. The Egyptians even had a name for this divine material, iron of the sky. It was rarer and more valuable than gold, reserved for pharaohs. This history matters because it establishes a fundamental contrast. Terrestrial iron ores almost never exceed 4% nickel. Meteoritic iron, however, is rich in it. The same questions our ancestors faced, what is this strange metal and where did it come from, are echoing today as we analyze the impossible alloys of 3I Atlas. Kilonova formation theory. So if not aliens, what could possibly create pure nickel vapor in space? The answer might lie in one of the most violent events in the universe, a kilonova. This is what happens when two neutron stars, the ultra-dense corpses of massive stars, spiral into each other and collide. The resulting explosion is so powerful, it forges heavy elements through a process of rapid neutron capture known as the R process. In 2017, the gravitational wave event GW170817 gave astronomers their first direct look at this process, confirming that neutron-star mergers create vast quantities of heavy elements like strontium, gold, and platinum. Nickel is also created in this cosmic furnace. Crucially, depending on the chaotic conditions of the explosion, some models predict that patches of the ejected debris can be exceptionally rich in nickel while being poor in iron. These aren't the slow-cooked metals from normal stars. They are forged in seconds and blasted into space. If 3I Atlas condensed from such a cloud of debris, it would carry a chemical fingerprint completely alien to our solar system. This provides a natural, albeit spectacular explanation for its strange composition. Asymmetric supernova theory. So, there's another natural forge out there in the cosmos, violent enough to potentially explain 3I Atlas's strange chemistry, an asymmetric supernova. You see, not all stars meet their end in neat spherical explosions. Some, well, they rip themselves apart in these lopsided blasts that fling elements out in jets. The supernova remnant W49b is a perfect example of this. X-ray maps from the Chandra Observatory show that iron is packed tightly near the remnant's core, while other elements like sulfur and silicon are distributed more broadly. This kind of uneven explosion, it completely changes the rules of how metals are scattered into space. In these chaotic events, the inner layers of the star, where iron and nickel are made, don't mix evenly. Instead, high-speed plumes can punch through the star's outer layers, carrying specific elements with them. And if nickel happens to be concentrated in the path of one of these jets, it can be ejected in bulk, leaving most of the iron trapped behind. So, if 3I Atlas formed from a fragment blasted out by such a supernova, it could have started its journey as a chunk of nearly pure nickel. This provides a second plausible, though very rare, natural path to its bizarre composition. Statistical improbability. Beyond its strange chemistry, the path of 3I Atlas through our solar system is so unusual it's hard to ignore. Avi Loeb and his collaborators ran the numbers, calculating the probability that a random interstellar object would have a trajectory that takes it unusually close to Venus, Mars, and Jupiter, all in a single pass. The result was a probability so small it's almost zero, about 0.005%. That's like flipping a coin 15 times and getting heads every single time. To Loeb, this really strains the definition of coincidence and starts to look like a pattern. The object's path is nearly flat relative to the solar system's plane, but it's moving backward or retrograde against the flow of the planets. This combination allows it to skim past the inner worlds in a way that looks suspiciously like a survey flight. Critics argue that in a vast universe, rare events are bound to happen, but Loeb counters that if the odds are 1 in 20,000, and we've only seen 3 interstellar visitors so far, something doesn't add up. When you combine this improbable trajectory with the engineered-looking metals, Loeb argues it's time to take the artificial origin hypothesis seriously. The Golden Record Parallel. Could 3I Atlas be a message in a bottle? In 1977, NASA launched the Voyager 1 and 2 spacecraft, each carrying a golden record. This was a project led by Carl Sagan, intended as a time capsule for any extraterrestrial civilization that might find it thousands of years from now. The records contain sounds and images of Earth, music from various cultures and scientific diagrams, a snapshot of humanity etched onto a durable physical object. Sagan said, "The launching of this bottle into the cosmic ocean says something very hopeful about life on this planet." Now consider 3I Atlas, an object loaded with alloys and compounds that don't fit natural recipes on a trajectory that seems too precise. The parallel is striking. What if its message isn't written in grooves on a record, but in the very ratios of its elements? A physical archive designed to survive a journey of millions of years. If its composition is intentional, then 3I Atlas isn't just a visitor. It's a courier carrying a record of another world's chemistry, and maybe even its technology. Atomic messages. What if we've been looking for the wrong kind of message? For decades, the search for extraterrestrial intelligence has focused on radio waves and light signals. But what if an advanced civilization chose to send a message encoded in matter itself? This is the provocative idea that the anomalies of 3I Atlas force us to consider. On Earth, scientists are already developing methods to store information using the ratios of isotopes in molecules, creating a kind of atomic fingerprint that can be read with a mass spectrometer. In biology, DNA stores vast amounts of information in a sequence of 4 chemical bases. Some theorists now wonder if the periodic table itself could be used as a sort of cosmic QR code. By arranging isotopes in a pattern that nature would never produce by chance, a message could be baked into a physical object. This message would be incredibly durable, immune to cosmic noise, and capable of surviving for billions of years. Spectrographs are now re-examining every bit of data from 3I Atlas, looking for these hidden patterns. The hunt is on for a fingerprint that says someone was here, and they wanted to be found. The story of 3I Atlas leaves us at a profound crossroads. On one hand, we may be witnessing an undiscovered violent natural process, a kilonova or an asymmetric supernova capable of creating alloys we once thought impossible. On the other hand, the combination of inexplicable metals, extreme chemistry, and a statistically improbable trajectory has forced serious scientists like Avi Loeb to consider an engineered origin. This isn't just a theoretical debate, it's a real object with real data that is breaking our models of the universe. Either way, our understanding has to expand. Don't forget to like, subscribe, and hit the bell icon for more deep dives into cosmic mysteries. Thanks for watching Space Facts. What if I told you the greatest journey in human history is about to get a sequel? For nearly 50 years, two probes, relics of the 1970s, have been our only eyes and ears in the vast dark ocean between the stars. But their time is running out. Now scientists are designing a successor, a true interstellar explorer built for the 21st century, powered by next-generation systems and guided by artificial intelligence. This is the story of humanity's next great leap into the cosmos, so let's explore this together. The original Voyager achievement. Ever wonder what raw discovery looks like? Picture this. It's 1977 and NASA launches two spacecraft, Voyager 2 on August 20th and Voyager 1 on September 5th. Their mission, led by longtime project scientist Ed Stone, was to exploit a planetary alignment so rare it only occurs once every 175 years. This grand tour would use gravity assists to slingshot from one gas giant to the next. What they sent back from their 23-watt transmitters about the power of a refrigerator light bulb redefined our universe. At Jupiter, they discovered the first active volcanoes beyond Earth on its moon Io and faint rings around the planet itself. At Saturn, they mapped thousands of intricate ringlets and flew by the haze-shrouded moon Titan. But Voyager 2 kept going, becoming the only spacecraft to ever visit the ice giants. At Uranus, it discovered 11 new moons and 2 new rings. At Neptune, it found 6 new moons and powerful 1,200-mile-per-hour winds. These weren't just flybys. They were foundational moments in planetary science, transforming our understanding of the outer solar system from distant points of light into complex, dynamic worlds. A journey into interstellar space. So what happens after you complete a grand tour of the outer planets? You keep going, farther and faster into the unknown. After their primary missions ended in 1989, the Voyagers began the Voyager Interstellar mission. Their new objective was to reach the edge of the heliosphere, the vast magnetic bubble inflated by our sun's solar wind that shields the planets from about 75% of galactic radiation. For years they traveled toward this boundary. Then on August 25, 2012, Voyager 1 made history at a distance of 121 astronomical units, or 121 times the distance from Earth to the Sun. It crossed the heliopause, the final frontier of our solar system, and entered interstellar space. Stamatios Tom Crimigis, a lead investigator, confirmed the data was undeniable. Voyager 2, on a different trajectory, followed suit on November 5, 2018, at about 119 AU. Now, Voyager 1 is over 163 AU away, the most distant human-made object in existence. For the first time, we were getting direct measurements of the interstellar medium, data sent from a place no probe was ever truly built to explore. Current limitations of the Voyagers. Here's the hard truth. The Voyagers are technological miracles, but they are also antiques from the dawn of the digital age. We're talking about spacecraft with a total of 69.63 kilobytes of computer memory, trying to send signals that take over 22 hours to reach Earth. Their data transmission rate is a painfully slow 160 bits per second, a speed that would make dial-up internet feel futuristic. Their instruments were state-of-the-art for the 1970s, but they were designed for planetary encounters, not the subtle environment of interstellar space. The biggest problem, as current project manager Suzanne Dodd often highlights, is power. The 3 radioisotope thermoelectric generators on each probe initially produced 470 watts of electrical power. Today that has decayed to under 250 watts and continues to drop by about 4 watts per year. To conserve every last drop of energy, the cameras were shut off in 1990 after taking the famous pale blue dot photo. Every year, more systems are powered down. Sometime around 2025 there simply won't be enough power to run any of the science instruments at all, and their historic journey will fall silent. The case for Voyager 3. With the original Voyagers fading, the question isn't just about continuing their legacy, it's about launching a revolution in interstellar science. The scientific community, including visionaries like Ralph McNutt Jr. from the Johns Hopkins Applied Physics Laboratory, isn't talking about a simple sequel. They're actually proposing a dedicated interstellar probe. This concept, which is often nicknamed Voyager 3, would be a machine designed from the ground up for a 50-year mission to explore the interstellar medium. It would carry a suite of modern instruments specifically built to analyze the space between stars with a precision the Voyagers could only dream of. The goal is ambitious: to travel 1,000 astronomical units from the Sun, more than 6 times farther than Voyager 1 has traveled in nearly 5 decades. This isn't about nostalgia for the Voyager name, it's about a critical scientific imperative. The Voyagers proved we could touch the stars, but they left us with more questions than answers. A new probe would be our tool to finally understand our place in the cosmic neighborhood. Advanced technology capabilities. So, how do you build a spacecraft for a 50-year journey to the stars? Well, you start with radical speed. A modern interstellar probe, as conceptualized by Ralph McNutt's team at APL, would need to travel much faster than the Voyagers. The plan involves a daring solar obirth maneuver. The spacecraft would dive incredibly close to the Sun, within 4 solar radii of its surface, where it would be subjected to immense heat and radiation. At its closest point, it would fire its engine, using the Sun's immense gravity as a slingshot to accelerate to speeds approaching 95 kilometers per second. That's about 20 astronomical units per year, nearly 3 times faster than Voyager 1's current velocity of 17 kilometers per second. This would allow it to reach the heliopause in just 15 years. To survive this maneuver, it would require a revolutionary new heat shield made of carbon-carbon composite. On board, AI-powered systems would handle navigation and fault management, making autonomous decisions light hours away from home. Power would come from next-generation nuclear systems designed for a 50-year-plus operational life, ensuring it could send back a robust stream of high-resolution data for decades. The interstellar medium mystery. Why is it so critical to study the space between the stars? Because our solar system is not an island, it's a ship sailing through the interstellar medium, and the heliosphere is our hull. For years we thought this protective bubble was shaped like a comet, with a long tail stretching behind it. But the data from the Voyagers, combined with models from astrophysicists like Merav Ofer of Boston University, suggests something far stranger. Her models indicate the heliosphere might be a deflated croissant or have 2 distinct jets, a shape no one predicted. The truth is, we don't know for sure because we only have 2 data points from the Voyagers. A dedicated interstellar probe with modern plasma and magnetic field sensors could finally map its true structure. It would directly measure the density of the local interstellar cloud our Sun is passing through, about 0.1 atoms per cubic centimeter, and chart the strength of the interstellar magnetic field. Understanding this interaction is fundamental to knowing our place in the galaxy and the nature of astrospheres around other stars. Scientific objectives and research goals. So, what specific questions would a new interstellar probe answer? Well, let's get into the hard science here. The primary goal, as laid out in the Interstellar Probe Concept Study, is to understand the heliosphere as a habitable astrosphere. By directly sampling the pristine material of the local interstellar cloud, it could actually determine the true composition and state of the galactic medium our solar system formed in. Second, it would map the magnetic field structure from the Sun all the way out into the galaxy, revealing how our local magnetic bubble gives way to the vast magnetic field of the Milky Way. This is critical for understanding how cosmic rays are filtered and accelerated. Third, from a vantage point hundreds of astronomical units away, it would be able to look back and image our entire solar system as a single system. It could observe the zodiacal dust cloud, the dust left over from the formation of our planets, and see how it glows, providing a vital ground truth for what telescopes like JWST are trying to observe around distant exoplanetary systems. All in all, it would bridge the gap between our home and the billions of other star systems in the galaxy. Practical applications for future missions. This isn't just about pure science, it's about laying the foundation for humanity's future in space. A modern interstellar probe would be a crucial pathfinder, charting the hazards of deep space. Its most important practical application would be creating the first detailed map of the radiation environment beyond our heliosphere. We know from Voyager data that the flux of high-energy galactic cosmic rays is roughly 3 times higher outside the heliosphere. These particles can damage electronics and pose a significant threat to biological life. A new probe would measure this radiation with unprecedented accuracy, providing the essential data engineers need to design shielding for future robotic and eventually, human interstellar missions. Understanding the plasma turbulence and magnetic field orientation is also critical for developing safe navigation strategies. Just as early sailors needed charts of ocean currents and reefs, future interstellar explorers will need a map of the interstellar medium. This mission would create that first map, making the next steps in exploration possible. Cultural significance and golden record 2.0. Beyond the science, there's the story of us. The original Voyagers carry the golden records, 12-inch gold-plated copper discs conceived by a team led by Carl Sagan, Ann Druyan, and Frank Drake. They are time capsules carrying 116 images and 90 minutes of sounds and music from Earth, from Bach to Chuck Berry. They are a message in a bottle thrown into the cosmic ocean. A new interstellar probe would carry this tradition into the 21st century. Imagine a golden record 2.0. Not an analog disc but a digital archive with terabytes of storage. It could contain the entirety of human knowledge, our science, our art, our music, our languages. It could carry a message crafted not just by a small committee but by humanity itself, perhaps even using AI to create a message designed to be universally decipherable. It would be a dynamic reflection of who we are now, a global, interconnected, and complex species. This probe would be both a scientific instrument and a cultural ambassador carrying the story of a curious species from a small blue dot into the vastness of the galaxy for eons to come. Timing and opportunity. Here's why this conversation is happening right now. The original Voyager's Grand Tour was a once-in-a-lifetime opportunity. To achieve the immense speeds needed for a true interstellar mission in a reasonable time frame, we need a similar advantage. As identified by Ralph McNutt and the APL team, a powerful launch window opens in the 2030s. A launch in 2036, using a powerful rocket and a Jupiter gravity assist, would provide the optimal trajectory to reach the target speed of 20 astronomical units per year. Missing this window would mean waiting until the next alignment in the late 2040s, a significant delay for a mission that is already decades in the making. The technology needed for the core mission is largely ready or in advanced development. This isn't a far-off dream, it's an achievable plan with a clear timeline. The Voyagers have been our scouts, but their journey is nearing its end. If we want to build on their legacy rather than letting it fade into silence, the time to commit is now. The cosmos is waiting, and the launch window is opening. From the revolutionary discoveries of the original Grand Tour to the tantalizing mysteries of interstellar space, the Voyager legacy has pushed the boundaries of human knowledge. Now, with concepts like the interstellar probe, we have the chance not just to continue that journey but to begin a new, bolder era of exploration. It would be a mission to understand our home in the galaxy, to test the limits of our technology, and to carry our story to the stars. The first Voyagers were our messengers to the cosmos. This next one could be our guide. Are we ready? Don't forget to like, subscribe, and hit the bell icon. Thanks for watching Space Facts. Could an object speeding through our solar system from the void between the stars actually be an alien spacecraft? On July 1, 2025, a mysterious visitor designated 3Y Atlas was discovered, sparking a fierce debate. Was it a natural comet, or the first definitive proof of extraterrestrial technology? One prominent Harvard scientist fanned the flames of speculation, while NASA pushed back with hard data. What followed was a clash between radical ideas and rigorous evidence. Let's explore this together. The Atlas discovery in Chile. So how do we even spot these interstellar travelers in the first place? It starts with a constant, vigilant watch of the night sky. The story of 3I Atlas began on July 1, 2025, at an observatory in Chile. There, a robotic survey system named ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, detected a faint object at an apparent magnitude of 20, making it about 2.5 million times fainter than the faintest star visible to the naked eye. Led by principal investigator John Tonry, the ATLAS system is a NASA-funded project developed by the University of Hawaii, using its twin half-meter telescopes to scan the entire visible sky every 24 hours. When astronomers calculated the object's trajectory, they saw it was following a sharply hyperbolic path with an orbital eccentricity greater than 1, a definitive sign it wasn't gravitationally bound to our sun. Its orbit was an open curve, meaning it came from deep space and was destined to return there. The object was named 3I Atlas, with the 3I marking it as the third interstellar object ever discovered. It was racing through our system at a stunning hyperbolic excess velocity of 35 kilometers per second, a truly exceptional catch and a prime target for immediate scientific study. Avi Loeb's controversial hypothesis. But what if a new discovery doesn't fit neatly into our existing boxes? This is where science can get heated. Enter Avi Loeb, a Harvard astrophysicist and the head of the Galileo Project, an initiative dedicated to searching for evidence of extraterrestrial technology. Having previously sparked debate by suggesting the first interstellar object, Oumuamua, could be artificial due to its observed non-gravitational acceleration, Loeb turned his attention to 3I Atlas. He pointed to its early lack of a visible tail and what he described as a trajectory that might eventually show subtle deviations not caused by gravity. In a paper released on the ArXiv preprint server, a common practice for rapidly disseminating new ideas, he proposed his radical hypothesis. If the object continued to show no outgassing, it might be a technological artifact. He even raised the hypothetical possibility of malign intent, suggesting it could use the sun for a gravitational slingshot to alter its course towards an undisclosed target. Loeb was careful to frame this as an intellectual exercise, admitting a natural comet was the simpler explanation. Still, the mere mention of alien technology from a scientist of his stature was enough to ignite a global media firestorm and put serious pressure on the astronomical community to respond. Media sensation versus scientific method. Here's the thing about alien theories. They travel faster than light speed in the media. Avi Loeb's hypothesis for 3I Atlas was sensational. Headlines around the world, from online blogs to major news networks, quickly latched onto the most dramatic elements of his proposal, the possibility of an alien craft with potentially hostile intentions. This created a fascinating public spectacle but also highlighted a fundamental tension in how science works. The scientific method is a slow, methodical process that can take months or even years of observation and peer review before any conclusion is reached. In stark contrast, the news cycle operates in mere hours. The global conversation was suddenly centered on a dramatic, unproven idea while the painstaking work of collecting hard data was just beginning. This put NASA in the position of having to respond not just to a scientific hypothesis, but to a worldwide media event fueled by one of the most compelling questions in human history. It was a classic case of exciting speculation, published on a preprint server before peer review, getting a massive head start on the deliberate evidence-based investigation. This gap between speculation and verification is where misinformation can thrive. NASA's comprehensive investigation. When a claim is that big, you really need the world's premier space agency to weigh in. So how did NASA approach the mystery of 3I Atlas? Well, they didn't rely on just a single instrument. Instead, they launched a coordinated, multifaceted observation campaign, allocating dozens of hours of precious observation time on their flagship observatories. This involved the Hubble Space Telescope, using its Wide Field Camera 3 to capture incredibly detailed visible light images, and the James Webb Space Telescope, using its NIRSPEC instrument to analyze the object's infrared light for chemical signatures. A network of powerful ground-based observatories, like the Keck Observatory in Hawaii with its massive 10-meter twin telescopes, also joined the effort to track it continuously. This wasn't just about taking pictures. The goal was a deep analysis under the guidance of experts like Dr. Karen Meech, a leading astrobiologist renowned for her work on distant comets. This comprehensive approach was designed to replace speculation with an overwhelming body of evidence. NASA's mission was clear: to determine, with the highest possible degree of scientific certainty, the true nature of this interstellar visitor and let the data tell the real story. Comet behavior confirmed. So what does a comet actually do when it gets close to the sun? The answer to that question was the key to solving the 3I Atlas mystery. As the object continued its journey inward, NASA's array of telescopes watched its every move. The findings were unambiguous. By late July 2025, as it crossed inside the orbit of Mars, 3I Atlas started to behave exactly like a comet. It developed a glowing coma, a fuzzy atmosphere of gas and dust, that eventually grew to over 100,000 kilometers in diameter. Soon after, it began to sprout a tail of dust and gas stretching for millions of kilometers, pushed away from the nucleus by the solar wind. Dr. Lori Glaze, director of NASA's Planetary Science Division, summarized the findings clearly, stating that the object was exhibiting all the classic signs of a comet, reacting to the sun's energy. Its initial lack of a tail was simply because it was too far from the sun for its ices to sublimate. The final verdict from the data was in, "It looks like a comet, and it acts like a comet." so there was no need for an exotic, artificial explanation when a natural one fit the observations perfectly. Chemical composition analysis. Here's what really matters. You can learn a lot about something by the light it gives off. Using a technique called spectroscopy, a team of astrochemists led by a figure like Dr. Stephanie Malam from NASA's Goddard Space Flight Center analyzed the chemical makeup of 3I Atlas. This process is like a cosmic fingerprint analysis, where light from the comet's coma is split into a spectrum, revealing the distinct signatures of the molecules within it. The analysis confirmed the presence of water ice, but it was the other volatiles that were truly telling. They found a carbon dioxide to water ratio of 0.6, nearly double the average for comets in our solar system. The data from JWST also revealed significant amounts of carbon monoxide and traces of diatomic carbon, the molecule responsible for giving many comets their distinctive green glow. Far from being evidence of artificial design, these unique chemical traits told a story of its origins. The high CO2 content suggested that 3I Atlas formed in a brutally cold region of its home star system, much farther from its parent star than where our own comets were born. It was a pristine sample from a truly alien yet completely natural environment. Trajectory and safety assessment. With all the talk of alien technology and malign intent, a critical question had to be answered. Was this object a threat to Earth? The bottom line is a definitive no. NASA's Jet Propulsion Laboratory, or JPL, used the global observation data to refine the comet's trajectory with pinpoint accuracy. Their calculations made public through the Center for Near-Earth Object Studies showed its closest approach to Earth would be a distant 1.8 astronomical units, which is roughly 170 million miles. There was never any risk of impact. The comet's orbit was also highly inclined at 60 degrees relative to the ecliptic plane, the flat disk where the planets orbit, meaning it was passing high above the main traffic of the solar system. Its perihelion, or closest approach to the Sun, was calculated to be a safe 1.5 AU, well outside of Earth's orbit. NASA's Planetary Defense Coordination Office was therefore able to declare with certainty that this object posed zero threat. This precise tracking dismantled any notion that the comet could be a danger, allowing everyone to focus on the science. Natural anomalies in cometary physics. But what about the unusual traits that sparked the controversy in the first place? It's important to remember that in astronomy, unusual does not automatically mean unnatural or artificial. Comets, even the ones from our own solar system, are, notoriously unpredictable. To provide some context, NASA pointed to historical examples like Comet 17P Holmes. Back in 2007, that comet suddenly brightened by a factor of nearly 1 million in less than 48 hours, totally shocking astronomers as it briefly became the largest object in the solar system by volume. This was a completely natural outburst, not an artificial maneuver. Cometary physicists like Dr. Michael Kelly from the University of Maryland explain that these events happen when sunlight penetrates a comet's crust and hits a pocket of super volatile ice, like frozen carbon monoxide, causing it to flash sublimate and release enormous amounts of gas and dust. These anomalies are not evidence of intelligent control, they are actually a normal and expected part of cometary physics. The strange initial behavior of 3I Atlas wasn't a sign of technology, it was a sign that it was a dynamic natural object. Scientific value of interstellar visitors. So, if it's not an alien ship, why is 3I Atlas still such a big deal? Well, because its scientific value is immense. Every interstellar object that passes through our solar system is like a pristine time capsule delivered from another star. These objects carry the unique chemical and physical fingerprints of the planetary nursery where they were born. The high concentration of carbon dioxide in 3I Atlas tells us it likely formed in an incredibly cold, distant region of its home system. Some studies even suggest it could have originated in the Milky Way's thick disk, a population of older stars, making the comet potentially over 7 billion years old, actually predating the formation of our own sun and planets. Scientists could test this hypothesis by analyzing its isotopic ratios, for instance, the ratio of carbon-12 to carbon-13, and comparing it to other stellar populations. That makes it more than just a passing rock. It's a preserved fragment from the dawn of another world, providing invaluable data for our models of galactic chemical evolution. comparing three interstellar objects. Let me explain why having more than one of these visitors is so crucial. By comparing them, we can start to build a bigger picture of the galaxy. 3. I-Atlas was the third interstellar object detected, and it's fascinating how different all three have been. The first, 1E Oumuamua, was highly anomalous, rocky, appearing to have an extreme 10:1 aspect ratio, and showing no visible coma, which is what led Avi Loeb to his original theory. The second, 2I Borisov, discovered by amateur astronomer Gennady Borisov, was almost the opposite. It looked and behaved very much like a standard long-period comet from our own Oort cloud, with a chemical composition, specifically a carbon monoxide to water ratio of about 0.3, that was remarkably familiar. 3I Atlas falls somewhere in the middle. It clearly behaves like a comet, but its distinct chemical ratios and light-scattering properties make it stand out as unique. This diversity is exactly what astronomers hope to find. It allows them to test whether the processes that shaped our home system are typical, or if we are, an outlier. In the end, Comet 3. I-Atlas wasn't an alien messenger, but it did bring an incredible message. It wasn't science fiction, but it delivered profound science. It carried the chemical secrets of its birthplace, a star system far from our own, giving us a rare glimpse into the diversity of worlds forming across our galaxy. The real story isn't about a manufactured object, but about the natural wonder of the universe and our growing ability to study it. If you want more deep dives into the biggest discoveries from space, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting for us. Thanks for watching Space Facts.